So we've previously looked at SN2 and E2 reactions. Now it's time to turn our attention to SN1 and E1 reactions. SN1 and E1 are alternate mechanisms for the substitution and elimination that we saw with SN2 and E2 reactions. Both SN1 and E1 are stepwise, right? This is different from the SN2 and E2 that are concerted, right? And when I say concerted, if we think about the SN2, we lost the leaving group and the nucleophile attacked in the same step. In the SN1 and E1 reactions, these happen in two separate steps. So first we lose the leaving group, and then the nucleophile attacks, or we have the proton transfer in the case of elimination, occurring in a second step. So for both SN1 and E1, they start with the same step, which is ionization of the substrate, or the loss of the leaving group. So for both SN1 and E1, the first thing that happens is the leaving group jumps off, and that leaves us with a carbocation intermediate. And then, in a subsequent step, in the case of SN1, the nucleophile will attack, or in the case of E1, the solvent will act like a base, pull off one of the beta hydrogens, and lead to an alkene. So SN1 and E1 reactions occur most frequently with tertiary substrates. That's because when we have this carbocation intermediate, it's going to be most stable in the case of a tertiary substrate. So if we consider the SN1 mechanism first, we're given the mechanism here, right? And so what happens is, again, first we have the loss of the leaving group. So in this case, we lose the bromide ion. We have the carbocation intermediate, and then the nucleophilic attack occurs to give us this substitution. And then in the case of a neutral solvent, where the product in this step has a charge, very often that's followed by a proton transfer. And so the entire mechanism is actually three steps, right? But the SN1 part is really considered these first two steps. Now, these first two steps is overall exactly the same process as an SN2 reaction. In the case of an SN2 reaction, however, it's just one step, and both the loss of the leaving group and the nucleophilic attack happen in the same step. In the case of an SN1 mechanism, they happen in two distinct steps. Very often, the SN1 and E1 reactions are called solvolysis because the nucleophile, or in the case of an E1 reaction, the base is also the solvent. So this slide shows a typical reaction energy diagram for an SN1 reaction. And you can see that we have indeed the three steps. So we start with the loss of the leaving group, then the nucleophilic attack, and then the proton transfer to give us our final product. And as you can see, it's the first step that has the largest activation energy. The barrier is the highest, so that means that this is the rate determining step. So the loss of the leaving group is the rate determining step in an SN1 reaction. Now, since the formation of the carbocation only requires the ionization of the substrate, and the nucleophile hasn't attacked yet, that means that the rate only depends on the concentration of the substrate. And so the name SN1 comes from the fact that it's a substitution. It involves a nucleophilic attack, right? But it's a unimolecular reaction. The order of the reaction is 1. Okay, now let's take a look at the E1 mechanism. And so in this case, we start with the same first step, the loss of the leaving group to form a carbocation. In this case, instead of having a nucleophilic attack in a substitution reaction, in this example, the ethanol is going to act like a base, and it's going to steal that hydrogen to give us an elimination product. Now, you may notice that this is the exact same substrate that we had when we looked at the SN1 mechanism, and it's the exact same solvent. It's just that the ethanol was behaving differently in the SN1 case versus the E1 case. And as is often the fact, we typically get both mechanisms happening at the same time, and so we'll often get a mixture of products. We'll get a mixture of both substitution and elimination products. And like an SN1 reaction, the E1 mechanism is unimolecular. So it's this loss of the leaving group that is the rate determining step that only depends on the concentration of the substrate, so it follows the same kinetics. And just like an SN1 was the same overall process as an SN2 reaction, the same thing is true here, right? In an E2 mechanism, it's just that the loss of the leaving group and the beta hydrogen elimination occur in one step, right? The difference is in an E1 mechanism, it takes place in two separate and distinct steps. All right, and so we have another reaction energy diagram here. And in this picture, they're actually showing us the relative energies for a competing E1 and SN1 process. And as you can see, right, the first step is rate determining for both, and it's the same first step. It's the formation of the carbocation. And then which products we get more of is going to be determined how high the transition state is for the second step. In this case, they've shown the SN1 transition state as being lower, and that is very often the case. It's not always the case, but it is frequently the case. But as I said before, we usually get a mixture of products from these reactions. Okay, so both the SN1 and the E1 reactions proceed through a carbocation intermediate. And we saw previously, when we looked at the patterns for these mechanisms, that one of the common patterns is carbocation rearrangement. And so SN1 and E1 reactions can often involve these carbocation rearrangements. And so if I look at this substrate, and if I heated that in the solvent water, we can actually get two different substitution products. So the reason we can get these two I have down at the bottom of the slide here, right? So for both of these substitution products, the first step is the loss of the leaving group to produce a carbocation. If the substrate gets attacked by the nucleophile at this point, it would lead to the first product, but this is a secondary carbocation. If I can do, in this case, a hydride shift, but methide shifts are also possible, right? I can convert it to a more stable tertiary carbocation. And so if this carbocation rearrangement happens before the nucleophile attacks, then it will lead to this product. So when you have a primary substrate, SN1 and E1 reactions are not very common, but they can happen. Now, in this case, if I look at this substrate, we might expect to have two possible products. So we can have the product that where we have an OH here, in this case, right, that doesn't involve rearrangement, and then also, right, I can have a methide shift to get the carbocation here, and so that would give me this product. Now, it turns out that this is the only product, and this second one is in fact not observed. Now, the reason being is that primary carbocations are extremely unstable, and so I can't just pull off the leaving group, leaving me with a primary carbocation. Instead, what happens is, at the same time the leaving group leaves, we have the methide shift. And so we don't ever form the primary carbocation. Instead, we directly form the tertiary carbocation, which can then be attacked by the water, the nucleophile, and then followed by the proton transfer to give us the final product. Okay, so we also want to consider how the solvent affects the rate of SN1 and E1 reactions. And the solvents affect both SN1 and E1 reactions the same because they have the same rate determining step, that is the loss of the leaving group. And so they've plotted a number of different solvents here along with their dielectric constants. And a dielectric constant is sort of a measure of the polarity. A larger dielectric constant corresponds to a more polar solvent. And then they also have them classified as being either protic or aprotic. And finally, they have the relative rates down here. And so you can see the reactions are fastest in the presence of polar protic solvents. And the more polar the solvent is, the faster the reaction is going to be. And so this is actually the opposite of SN2 reactions. If you remember, SN2 reactions favor aprotic solvents, whereas SN1 and E1 reactions favor polar protic solvents. So I think we can rationalize the difference in how the solvents affect the SN2 reactions versus the SN1 reactions is by looking at these reaction energy diagrams. And so in the case of SN2 reactions, the protic solvents greatly stabilize the nucleophile, right? And that means the nucleophile is less reactive. And so stabilizing that nucleophile lowers the energy of the reactants, and that effectively increases the activation energy. Whereas when we use polar aprotic solvents, they're not as good at stabilizing the nucleophile. That raises the energy of the reactants, effectively giving it a smaller activation energy and a faster rate. In the case of SN1 reactions, they don't depend on the nucleophile as much, right? They're governed by the first step, which is the loss of the leaving group. And because the leaving group and the resulting carbocation have charges, right, they are more stabilized by polar protic solvents. They can undergo hydrogen bonding to help stabilize them. So being in a protic solvent lowers both the activation energy and the energy of the intermediates, right? But the main thing is, right, it lowers the activation energy, yielding a faster reaction. All right, now the substrate can also affect the rate of SN1 and E1 reactions. And so we've shown the relative rates of the different halides. So as we go fluorine, chlorine, bromine, and iodine, they get more reactive. And the way we can rationalize this is when these react through SN1 and E1 reactions, right, since we're popping off these leaving groups, and so the more stable the leaving groups are, the faster the reaction is going to be, right? And so for I minus or Br minus or Cl minus to be stable, right, we want them to be stable or weak bases. And so if we think about when we talked about the stability of bases, right, we used ARIO, right? And so the bigger the atom was, the more stable the base was. So I think it makes sense that iodide would be the best leaving group and therefore is the most reactive and results in faster SN1 and E1 reactions. Okay, so not only does the nature of the leaving group affect the rate of the SN1 and E1 reactions, but also the stability of the resulting carbocation intermediate affects the rate of the SN1 and E1 reactions, right? And so tertiary carbocations are going to result in the fastest reactions, and oftentimes sulfolysis reactions involving primary and secondary alkyl halides, the carbocation is too unstable, making the reaction too slow to observe. Of course, we did see earlier that they can undergo carbon-cation rearrangement, which may speed up and make those processes more likely. But in general, it's tertiary alkyl halides as well as benzylic or allylic halides that are going to be most likely to react in SN1 and E1 reactions, because while these are primary carbocations, we're going to be able to draw resonance structures which stabilize these guys and allow us to spread that positive charge around the molecule. So the substrates that are most favorable for SN1 and E1 reactions are those that lead to tertiary carbocations or carbocations that can be stabilized by resonance. Now, just like we saw for E2 reactions, it is possible for E1 elimination to yield more than one constitutional isomer. So if I consider this substrate, right, I have two different types of beta carbons, right? We can either pull a hydrogen off one of these methyl groups, or we can pull a hydrogen off this CH2 group. And so that gives us two possible elimination products, as well as the substitution products. So when we have these sulfolysis reactions, we often get a lot of different products, and we get a mixture of products. Now, in the case of E1 reactions, right, we would expect this to be the more stable elimination product because it's the more highly substituted alkene, and we'd expect this to be the minor elimination product. And so this is similar to E2 reactions, but with E2 reactions, we could actually control how much of the Zaitsev or the Hofmann product we got by changing the base. Because the rate of E1 reactions only depends on the concentration of the substrate, we actually lose the ability to control which product we get. And so in some sense, that makes predicting the products of E1 reactions a little bit more simple. The more substituted constitutional isomer is always going to be the major product. All right, now also like E2 reactions, E1 reactions can be stereoselective. And so if we can produce both the E and Z isomers, we will, but generally one of them will be a major product and the other one will be a minor product. So if we consider this substrate, we have two different beta carbons. We've got the methyl group, and then these two CH2 groups are equivalent. If I eliminate the hydrogen from this beta carbon, that's going to give me this alkene. If I eliminate a hydrogen from either one of these two CH2 groups, I can get the E and Z isomers. So, right, I can get this would be an example of an E isomer, and then this would be the example of the Z isomer. But in this case, right, we would use steric considerations to determine what are the major and the minor products. So I think we'd see more of both of these than this one, because these are both tri-substituted, where this one is only di-substituted. So I think we'll see this product, elimination product, the least. And then when I compare these two, if I consider this the steric hindrance, here I have a methyl group bumping into a methyl group, and I compare that to the methyl group bumping into an ethyl group. So this is going to have more steric hindrance, and so this should be the major elimination product. And so again, E1 reactions are stereoselective, right? But we're going to get a mixture of a lot of different products. So in this case, we're going to have a mixture of the three different elimination products and the substitution product. Okay, finally, we want to consider the stereoselectivity of SN1 reactions. So if you remember, in the case of SN2 reactions, we have the backside attack that results in the inversion of configuration. And so we only see the inversion of configuration product. In the case of SN1 reactions, because we're going through this carbocation intermediate that is essentially planar, the nucleophile can attack from either side. In principle, it can attack either side equally, and so we actually get a combination or a mixture of both configurations, both where we retained the same configuration, which we would not see in an SN2 reaction, or the inversion of configuration, which is the same as what we'd get in an SN2 reaction. So in an SN2 reaction, we always get inversion of configuration. In an SN1 reaction, we get both products because the nucleophile can attack the carbocation from either side. Now, even though we do get a mixture of configurations in SN1 substitution, it turns out the inversion product is typically observed more than the one that retains the same configuration. And the typical explanation for that is when or after I've lost the leaving group, oftentimes the carbocation and that leaving group, where the carbocation is positively charged, that leaving group is negatively charged, they often form an ion pair. And so they kind of stick close together to each other for a while, right? And so if that leaving group is hanging around, if it's not getting completely lost, right, that prevents the nucleophile from coming in, right, where the nucleophile is free to come in on the backside. And so in SN1 reactions, we see both the inversion product and the one that retains its configuration, but we typically see a little bit more of the inversion product.